afternoon everyone. Myself Dipika Sarkar, Assistant Professor, Department of CSE AIML, Haldia Institute of Technology. In today's lecture, I will discuss about single source shortest path problem, which is a variation of shortest path problems. Now first of all, let's understand what is shortest path problem. Suppose when we want to travel from one place to another, we will opted for the shortest distance, right? We will opted for the path which will cover the shortest distance, obviously, so that the path cost gets minimized, right? So based on that idea, this particular problem, single source shortest path problem, have been implemented using the Bellman-Ford algorithm. Now before going to the details of this Bellman-Ford algorithm, let's understand what actually is single source shortest path problem. Single source shortest path problem says we have to find out the shortest distance from a particular source vertex to every other vertices of a given graph. Yes, graph. So that means what? Single source shortest path problem can be implemented using graph. Now what is graph? From the basics, we can say the graph is a set of vertices, edges and corresponding weights of the edges. Okay, so a graph is a set of vertices, edges and weights. So now let's see what is Bellman-Ford algorithm. So before going to start, let's understand what is the algorithmic strategy that Bellman-Ford works on. The algorithmic strategy is dynamic programming approach. What is dynamic programming? Dynamic programming says that divide the main problem into smaller sub-problems, then find out the solution of the smaller sub-problems and collect all the solutions from all the solutions of the sub-problems to make the ultimate solution of the main problem. So that is the idea of dynamic programming approach. So based on that idea, Bellman-Ford algorithm works. So let's see how it works. Okay, before going to start, this is an example graph. You can see this is the graph here. This is the graph. So this circle, all the circles are named A, B, C, D, E, F. These are the nodes of the graph, nodes or vertices, that is V of the graph. Okay, and all the red marked lines, these are the edges of the graph, and all the weights, this 6, 4, 5, -2, -1, these are all weights associated with the edges of the graph. Okay, so to understand Bellman-Ford algorithm, let's assume this graph and this particular node, that is A, as the source node. Okay, so we have to find out the shortest distance from this particular source node A to B, A to C, A to D, A to E and A to F. Okay, now how will we solve it? We will solve it using Bellman-Ford algorithm. The algorithm has been depicted here. Okay, so I will come later on to this algorithm. Now first of all, let's understand the working. Okay, so this is the given graph. Now the Bellman-Ford algorithm says, relax all the edges till n-1 times. Okay, so relax all the edges till n-1 times. What is n? N is the number of vertices. What is relax? What is relaxation? Relaxation, we can say we have to iterate the process till n-1 times. So for this given graph, there are 6 vertices. So we will do the process till 5th time. Okay, so in the first step, what we will do, we will list down all the direct edges. We will list down all the direct edges. Okay, so one by one we will list down. A to B, there is a direct path from A to B, as you can see the direction. Okay, A to C, A to D. Okay, and next we are done with the A, and then we will take this vertex B and we will see what are the direct edge from B. Okay, so from B it is B to A, no, B to C, no, B to D, no, there is no direct path, B to E, yes, so B to E is there. And B to any other vertices, B to F, no. Okay, now let's start with C. C to A, there is no path from C to A because see, you can see the direction is in other way. C to B, yes, there is a path from C to B. C to B. C to D, no, there is no path from C to D. C to E, yes, there is a path from C to E. C to F, no, there is no direct path from C to F. Okay, we are done with C. Next D. From D to A, there is no path from D to A. D to B, there is no path. D to C, yes, there is a path from D to C. And D to E, there is no direct path, and D to F, there is a path. Okay, so D to F. Now from E, see, from E, only E to F is the only direct path. E to F. Okay, I am writing it here. E to F. And the next and the last one is F. F to any other vertices, direct path? No, there is no direct path from A to any other vertices. So okay, so we have listed all the edges. We have listed all the direct edges. Okay, direct paths. Now what we will do, this is the source vertex. Okay, so we have to find out the distance of this particular node. So distance from A to A is what? 0, obviously. Okay, now let's suppose initially we will set distance from this particular source A to all other vertices is infinity. Okay, is infinity. Okay, because why it is set as infinity? Because initially we don't know the shortest distance from the particular source node A to all other vertices. So that is why it has been set to infinity. Okay, now we will apply the algorithm here. So the algorithm says what? If there is a path U to V, if there is a path from U to V, suppose in this example A is U and V is what? B. So we have to find out the distance of V. If the distance of V is greater than distance of U plus weight of U and V, if it is greater then the if the already distance of a particular vertex, suppose the node B, vertex of node B, if it is greater than the distance of U plus the associated weight or cost of that path, then we will update dV, with d of U plus weight of U comma V or cost of U comma V. So we will use this formula to find out the distance of every vertices. Okay, fine. So in our case it was what? A was U and B is what? V. Okay, so distance of V, so distance of B is what? Infinity. Now what is distance of U or distance of A? That is what? 0, right? That is what? 0. So 0 plus weight of U comma V, weight of U comma V. What is U? A. What is V? That is B. So distance of U comma V, that means weight of U comma V is what? 6. Okay, associated cost is 6. So 0 plus 6 is 6. Now whether this 6 is less than this infinity? Yes, obviously. So we will use this path to reach to B from A, okay, instead of infinity. Fine. So we will update infinity with 6. The similar process goes with this. When we are considering C as the destination vertex, this, if one particular vertex is source, then another is destination, suppose. So distance of C is what? Infinity, right? So that means distance of U, that is distance of A, is 0 plus cost, associated cost is 4. So 0 plus 4, that is 4. Now 4 is less than infinity, so we will update with 4. Okay, now next is what? A to D. So it is infinity. So and if we use the formula, then it is what? 0 plus 5, that is 5. So 5 is less than infinity. So we will update with 5. Fine. Now we are done with this and this. Now next is what? B to E. B to E. Okay. So the distance of E is what? Infinity. And B to E. So that means U is what? B and V is E. So distance of E is infinity and distance of U is what? 6 plus minus 1. Okay. 6 plus minus 1, that is 6 minus 1, that is 5. So 5 is less than infinity. So we will update with 5. We are done with B to E. Now next is what? C to B. C to B. So what is the distance of B? Distance of B is 6. Okay. And distance of B is 6. And what is distance of U? That is 4. And what is the associated path cost? That is minus 2. So 4 plus minus 2. 4 plus minus 2, that is 4 minus 2, 2, and the already distance is 6, which is greater than 2. So we will update with 2. Fine. So we are done with C to B. Now next is what? C to E. C to E. So what is the distance of E? That is 5 and distance of C is what? 4. So 4 and the associated path cost is 3. So 4 plus 3, which is 7, right? So 7 is obviously greater than 5, so we will not update it. Okay. So it will be 5 only. Now next is what? D to C. D to C. So C, distance of C is what? 4 and distance of U is 5. So and associated path cost is what? Minus 2. So 5 plus minus 2. 5 plus minus 2, that is 3. 3 is smaller than 4. Okay. So we will update with 3. D to C, we are done with D to C. Now next is what? D to F. D to F. The distance of F is infinity and distance of U, that means D, is 5 plus the associated cost is minus 1. So 5 plus minus 1. 5 plus minus 1, that is 4. So we will update infinity with 4. So done with D to F. Next is what? E to F. So 5 minus, sorry, the distance of F is 4 and a distance of U, that is distance of E, is 5 and associated cost is 3. So 5 plus 3 is 8 and it is already 4. So 4 is minimum. So we will not going to update it. Okay. So we were done with the first iteration, relaxing for the first time. Sorry. Relaxing for the first time. We are done with relaxing for the first time. Okay. Now next what we will do? Okay, relaxing for the first time. Now we will do for the second time relaxation. Okay. Now second time we will again do the same procedure for the second time. Okay. Now see, A to B, if we consider A to B, so the distance of B is 2 and if we consider U 0 plus 6, that is 6. So 6 is greater than 2. So we will keep 2. We are done with A to B. Now A to C. So distance of C is 3 and if we use A to C with 0 plus 4, that is 4, which is greater than 3. So we are not going to update. So we are done with A to C. Next is what? A to D. The distance of D is 5 and 0 plus 5, 5, which is same. So we are not going to update it. Next is what? B to E. Okay. B to E. So distance of E is 5 and if we consider B as U, then distance of U is 2 and the associated path cost is minus 1. So 2 plus minus 1. 2 plus minus 1, that is 2 minus 1, 1. Okay. Now 1 is minimum. So we will update 1. Update with 1. Okay. So we are done with B to E. Next is what? C to B. C to B. Now distance of B is what? 2. Okay, and if I find in this way, distance of PU, that is C, is 3. So 3 plus minus 2. 3 plus minus 2, that is 1. Okay, so 1 is less than 2. So we will update with 1. C to B. Now next is what? C to E. C to E, the distance of E is 1 and the distance from C, that means U is 3 plus 3. The path cost from C to E is 3. So 3 plus 3 is 6. So 6 is greater than 1. So we will not going to update it. Okay. We are done with C to E. Next is what? D to C. So D to C. So distance of C is 3 and distance of D is 5 plus minus 2, that is 3 only. So no change. Okay. Next is D to F. D to F, the distance of F is 4 and the distance of D is 5. So 5 plus minus 1, that is 4 only. So these are same. So no updation required. Next is E to F. So E to F, distance of F is 4 and if we consider E as U, then distance of U, that is 1 plus 3, that is 4. 4 only, so no change. Okay, so we are done with the second iteration. Okay, so we can observe, we have observed that there were some changes in the second iteration. That means there were some path cost updation in the second iteration as well. Now let's do with the third iteration. Okay, again we will do the same procedure. So A to B was 1 and if we go this way, then 0 plus 6, so 1 is minimum, we will keep at it as it is. Then A to C, it is 3 and 0 plus 4, so 3 is minimum, so no change. A to D, the distance is 5 and 0 plus 5 will be same, so no change. Okay, now B to E. B to E. So the distance of E is 1 and if we go from B to E, then it will be 1 plus minus 1. 1 plus minus 1, that is 0. Yes, so 0 is less than 1. So we will update with 0. So we are done with B to E. Next is what? C to B. Okay, C to B. So the distance of B is 1 and if we go this way, then 3 plus minus 2. 3 plus minus 2, that is 1. So same only. So there will be no change. C to B. Next is what? C to E. Okay, so the distance of E is 0 and if we consider this, then 3 plus 3, which is 6, which is greater. So no updation required. C to E. We are done with C to E. Next is what? D to C. D to C. So distance of C is 3 and if we consider D as U, then it will be 5 plus minus 2, that is 3, the same only. Okay, so no updation required. D to C. D to F. So it is 4 and 5 plus minus 1 is 4 as well, so no updation required. And E to F. The distance of F was 4 and now distance of E is 0 plus associated cost is 3. So 0 plus 3, which is 3, which is less than the previous one. Okay, so we will update it with 3. Fine. So we are done with all the edges. Okay, and in this way our third iteration got completed. So you can see in the third iteration as well, 2 updation was there. 2 updation was there, right? Now we will go for the fourth iteration. Let me change the color. We will go for the fourth iteration. In the fourth iteration, we will do the same procedure again and see it was 1 A to B, the distance of B is 1. So it is what? If we consider U as A, then 0 plus 6, so 6 is greater, so no change. A to C, distance of C is 3 and 0 plus 4, that is 4, which is greater, no updation. A to D is 5 and A to D is 5 as well, 0 plus 5, no updation required. Next is what? B to E. B to E. So distance of E is 0 and 1 plus minus 1 is also 0. So no updation required. Okay. Next is what? C to B. C to B. So C to B is distance of B is 1 and if we consider C as U, then it will be 3 plus minus 2, that is 1 only. So the same value, so no updation required. Next is what? C to E. C to E, the distance of E is 0 and distance of C is 3 and path cost is 3. So 3 plus 3 is 6. No need to change because 6 is obviously greater than 0. Fine. And then next is D to C. So distance of D is 5 and distance of C is 3 and distance of 5 is D is 5 and the associated path cost is minus 2. So 5 plus minus 2 is 3 and it is already 3. So no need to update. So D to C, we're done with D to C and next is what? D to F. So distance of F is 3 and distance of D is 5 and the associated path cost is -1. So 5 plus -1, that is 4. Okay, so 3 is already shorter, smaller than 4. So no need to update D to F. Now E to F. Okay, so the distance of F is 3 and distance of E is 0 plus associated cost is 3. So 0 plus 3 is 3 only. Okay, so no need to update. Okay, so we are done with the fourth stage as well. Okay, let me point out the previous one. Yes. Okay, so you can see we are done with the fourth stage as well. Now you see in the fourth stage there was fourth iteration, there was no update in the distances, right? There was no update in the distances. Fine, but we have to relax the edges maximum n minus 1 times, up to n minus 1 times. Okay, so the process will continue till n minus 1 time, that means for the fifth time as well, for the fifth time as well. So if you do the same process for the fifth time, you will see that there will be no change. Okay, I am not doing this right now. So if you do the same procedure for the fifth time as well, you will see there will be no changes in the distances. Okay, so this is how you have actually calculated the shortest distance from a particular source to every other distances. How? See, from A to B the distance is 1. Okay, from A to C the distance is 3. From A to D the distance is 5. From A to E the distance is 0 and it is via B. Yes, so it is via B. So distance is 0. So from A to F it is what? 3, and I guess it is via I guess it is from with this path. Yes, I guess it is with this path. Fine. So what we have seen? We have seen that we have found out the shortest distance from a particular source to every other vertices, but not directly. So what we have done, we have first of all we have found out the solution of the sub problems for the intermediate nodes. Okay, and then only we can ultimately we have ultimately got the actual solution. So this is what Bellman-Ford algorithm. Now let me discuss another aspect of Bellman-Ford algorithm. In the Bellman-Ford algorithm, it can detect negative edge weight cycle, right? So what is negative edge weight cycle? If a particular graph contains a cycle and the summation of all the edge weights are negative, then we will call it as negative edge weight cycle, right? So suppose let's suppose this, consider this particular graph, as in the earlier graph there was no cycle. If you observe, there was no cycle present in the earlier graph, but it doesn't mean that Bellman-Ford will not work if a particular graph contains cycle. If a particular graph contains cycle, then also Bellman-Ford will give you the correct result. But if it is containing negative edge weight cycle, then only Bellman-Ford can detect it, and it will not give you the correct result. For example, let's suppose this is another graph. You can see in this particular graph a cycle is present. Cycle is present, right? From 2 to 4, 4 to 3 and 3 to 2. And the summation of the edge weights are what? 5 plus 3 plus minus 10. That means if you sum up all the edge weights, it will be minus 2. Okay, it will be minus 2. That means what? A negative edge, this is a negative edge weight cycle. Now, if you apply Bellman-Ford algorithm here, you will see that means Bellman-Ford algorithm will relax up to how many times? Because there are 4 vertices, so it will do up to third iteration, right? N minus 1, so n is 4, so it will do 4 minus 1, that is up to third iteration. But if you apply the algorithm for this particular graph, you will see after third iteration, that means in the fourth iteration as well, you will see the distances got changed. Distances are getting updated. That means what? It is not giving you the correct result. Okay, so these are some aspects of an important aspect of a Bellman-Ford algorithm. So here you can see the algorithm. Fine. So this is initialize single source G comma S. G is the graph, S is the source vertex. Now for I equal to 1 to set of V minus 1 do. So set of V minus 1 means number of vertices. Okay. So from 1 to n minus 1 times. So for each edge u comma v belongs to E is what? The set, edge set. Okay. If u v belongs to the edge set, then relax u comma v comma w. So this is the relaxation algorithm for the relaxation. So here is the, you know, that the calculation what we have used to find out the distance, right? If d of v greater than d of u plus weight of u v, then obviously update the minimum one, update with the minimum one to find the distance of v. Okay. And okay, fine. Now for each vertex v belongs to u comma adjacent, u dot adjacent, do this one. This is for what? This is to determine the negative edge weight cycle. So this is the algorithm for finding out the shortest distance, shortest distance from a particular source to every other node. Now coming to the time complexity of this algorithm, what should be the time complexity? Let me see you. Let me show you. The time complexity says it is E, set of E and V. Okay, so E is what? If we consider for any graph, E is you know, the number of edges n. So we have to relax it up to n minus 1 times, right? Up to n minus 1 times. Now if you find out, you will see one term will be n square, right? N square minus n. So this is the highest degree term. So we can consider the time complexity is big O of n square. Okay, big O of n square. Now this is what? This is the best case. Now what is the worst case then? Worst case is when the graph is a complete graph. In case of complete graph, what is the number of edges? The number of edges is n into n minus 1 by 2, n into n minus 1 by 2. And if you relax it till n minus 1 times, if you know, calculate it, then you will see the highest degree term will be here, n cube. I am not writing the other portions of the calculation, that means I am not bothering about the mathematical calculation, but to find out the time complexity, you will see the highest degree term you will get from here is n cube. So you can see the time complexity of this algorithm is n cube. Thank you.